very, I'm very happy to introduce Alan McDonald from the Department of Physics at University of Texas in Austin. He's an expert in electron-electron interactions in electronic systems, reduced dimension. He did his early work at the National NRC of Canada Research Labs and at Indiana, I'll speak English soon, University. He really has made important contributions to the field. There's always shown an interest in what's happening with the experiments, both to understand what just happened and also tell us experiments what we ought to be doing in the future. He won a number of awards, including the 2007 APS Buckley Prize in Condensed Matter Physics for the theory of correlated many electron states in low dimensional systems. A very important recent development was the discovery of superconductivity and also mod insulator states in magic angle twisted graphene, something at least personally I didn't expect, but I think maybe Alan McDonald did. And he won the 2020 Wolf Prize in Physics along with Rafi Bistritzer, I'm sorry if I'm not saying it right, and Pablo Guerrero at MIT for the experiments. This was a really big discovery because Alan said that if you make a twisted material at the magic angle, that the energy bands go flat and the correlation effects all turn on in a big way, which turned out to be really true. So I look forward to hearing his talk. Please think of good questions you can ask him at the end. So please get started. Thank you.
Okay, thanks, Bob. Please feel free to interrupt me at any time. As Bob said, and as many of you, my friends there know, this is a subject that I got interested in from experiments some years ago, working with a postdoc, Rafi Bistritzer, and a student, Fengcheng Wu. Rafi's now at Applied Materials in Israel, and Fengcheng is at the USTC in China. And thanks to experimental advances that most of you will be aware of, the subject has suddenly become extremely interesting. And so I've been drawn back into it, and I'll mention work by some of the names on this list as I go along. So my talk is going to be just about magic angle twisted bilayer graphene. I'm very much entertained these days with the gradually being revealed truth about what's going on inside the system. So I'm going to try and tell you what lessons I've taken away from some of the experimental data that's available on these systems. It's a little bit like reading tea leaves because as you'll see, I don't have all the conclusions I want to share are kind of soft and ambiguous. So what I have to say may actually not be much more useful than reading tea leaves, but I do have the feeling that people are making progress in this subject area. So magic angle twisted bilayer graphene is now part of a larger subject, sometimes referred to as moiré materials. The word moiré, according to Wikipedia, has the same root as the name of the wool of this beautiful sheep, mohair wool. But as a technical term, it's a very familiar term in electron microscopy, where it refers to interference between overlaid similar regular grid patterns, and that's the sense in which that's the type of moiré pattern we're interested in. And in particular, in moiré materials, we're interested in two-dimensional crystals, two or more two-dimensional crystals overlaid with small difference between their periodic patterns. For example, differences in orientation or differences in lattice constant. And if those differences are small, then there's a super periodicity that appears on a longer length scale. And it's that super periodicity that is clear here in this two overlaid honeycomb lattices, one red and one blue, that what you see is, with your eye, is that the stacking arrangement between the two layers gradually changes as you move through space, from crystals locally being right on top of the honeycomb lattices being locally right on top of each other at these lattice points with AA stacking to some AB stacking and back to AA stacking in a periodic way. So that's an example of a periodic pattern. And what we're interested in is the influence of this periodic moiré potential on electronic properties, and particularly so in the case of semiconductors and semimetals, when the electronic states we're interested in are all very close together in momentum space. And because of that, they cannot resolve what's going on an atomic length scale. And all of their electronic properties just depend on this slower, controllable periodicity from the moiré pattern. So these moiré materials act like two-dimensional crystals. One of the aspects of these artificial two-dimensional crystals that I think is actually extremely interesting, maybe more interesting and important than what I'm going to talk about today, is using these two-dimensional crystals to simulate real crystals. For example, there's been an effort, as you know, to simulate two-dimensional Hubbard models, which are thought to be superconductors, using cold atoms. So there's a very real prospect that it will be possible to do these simulations much better with moiré crystals, and to, for example, answer the question, is a two-dimensional Hubbard model a superconductor or not? And therefore the explanation for cuprate superconductivity, let's say. So moiré materials are interesting because they really seem in many cases to be the techniques that experimentalists have developed, many of you perhaps, allow them to be really quite nearly perfectly periodic. The typical size of an effective atomic unit cell of the systems that people simulate are on the tens of nanometer scale, linear scale, maybe 100 times or so more than a real atomic crystal. And that in a 2D system, that's very important because it allows you to change the number of electrons per effective atom of these artificial crystals by numbers of order 1 with just electrical gates. So you don't have to introduce dopants to change the number of electrons. And that really is very attractive from the point of view of fundamental studies of electronic properties of crystals. It's also, as I'll explain, possible to vary the bandwidth in different cases, and therefore go from case in which bands are broad and the single particle physics of electrons in those broad bands controls the physics, to the regime where bands are narrow and all of the properties are very strongly influenced by electronic interactions and correlations. As I said, one of the types of system of interest is starting from two-dimensional semiconductors, especially hetero bilayers of transition metal dichalcogenides, in which there turns out at the top of the valence band of such a system, there's just two spin states for each momentum, so it maps perfectly onto a one-band Hubbard model. And I think if people can make good enough systems and get to the correct regimes of twist angle, it should be possible to experimentally answer the question of whether two-dimensional Hubbard model is a superconductor or not. And so that's one thing that I hope is in the future, but it's not what I'm going to talk about today. I'm going to talk about magic angle twisted bilayer graphene, which doesn't simulate anything other than itself, perhaps, and but has shown already a number of intriguing things, and including orbital magnetism, and as Bob mentioned, superconductivity, and mod insulator states. And I'll try to say something about what we may be starting to understand about magic angle twisted bilayer graphene. So graphene is, in its bilayer graphene, when I form a moiré pattern, is more complicated than a hetero bilayer of two-dimensional semiconductor. Here is the familiar electronic structure of a single sheet of graphene, familiar to most of you. There are two bands of interest at low energies, pi electrons corresponding to pi electrons on the two sublattices of graphene's honeycomb. And in a bilayer, there are two layers, so that means every wave function is a four-component spinner with components on two sublattices and on two layers. And what's more, there are all of the low energy states have, in addition to a spin degree of freedom, they have a Valley degree of freedom. They can be identified as being close either to one of these two Brouin-Zone corner momenta, K and K prime here, related by time reversal. And so every electron wave is a four-component spinner, and it has four flavors for spin and valley. And I actually became interested in twisted bilayer graphene many years ago. There was some activity, some experimental activity related to accidentally discovered twisted bilayers, which are a common type of defect. For example, in graphite, there are always slightly misaligned layers, and I actually started on this from photo emission experiments I didn't understand, and we came up with working with Rafi Bistritzer with a simple picture, simple model of the electronic properties of twisted bilayer graphene, in which the two graphene layers influence each other only by tunneling between layers, and that the sublattice dependent tunneling between the two layers was a smooth function of position corresponding to the local stacking between the two layers. And the surprising thing about that model, which has since been explained better by Ashvin Vishwanath and collaborators in your university, is that at a certain set of discrete twist angles, most robustly near around 1 degree, the bands close to the Fermi level, a conduction valence band pair, a pair of bands each fourfold degenerate, as I was saying, became extremely flat, and mostly, except for small regions of momentum, and I'll come back to this later, well separated from by about 1/10 of a volt, which is a high energy scale for this purpose. Mostly, well, this flat band is well separated from the remote bands, and anywhere between -4 and +4 electrons per moiré period in this twisted bilayer, the Fermi level lies in the middle of these flat bands. And one could anticipate that if you could twist a bilayer to such a twist angle, you would get interesting, strong correlation behavior. And in 2010, nobody really knew how to do that. But as the years went on, techniques were developed. My colleague Emmanuel Tuta played an important role in that. And eventually, the experiments I showed you before were, which I should have explained, but are false color images of resistivity versus temperature and twist angle, were performed by Pablo Herrero Herrero with samples with well-controlled twist angles at low temperatures, and discovered insulating states and superconducting states separated in carrier density by less than a part per thousand in terms of number of electrons per carbon atom. So that's my topic. What have we learned since Pablo's discovery a couple of years ago about magic angle twisted bilayer graphene? And so in my talk, I'm going to talk a lot about one thing I think that is now pretty well established, and that is that magic angle twisted bilayer graphene has all over the place states that break these spin and valley flavor symmetries, and they do it in a particular way, and that's a lot of what I'm going to talk about. Okay, so I think a good place to start telling this story there, which has two parts. One is broken flavor symmetries, and the other is spontaneously open gaps. And so a part of what happens in magic angle twisted bilayer graphene is known from just AB Bernal bilayers and trilayers, and which have, as you may know, also have very flat bands, but bands that are continuously connected in momentum space out to high energies, but they're very flat at small momentum. And what I'm showing here is a picture of the band states as a function of 2D momentum. On the left-hand side, there are band states of for AB stacking, which is the thermodynamically stable stacking, bilayer graphene. This is sort of in this picture, a sort of block sphere representation of the band states of bilayer graphene. Turns out the low energy states are a linear combination of the two layers. In this case, only one sublattice is relevant in each layer. And so these arrows represent the coherence angle between the two layers. And the color scale represents whether or not the band states are layer polarized. And so when you look at the parabolic band touching as occurs in the band structure of bilayer graphene without interactions, it's easy to see that this band configuration is very susceptible to opening a gap, and it does so, in fact, certainly in any kind of mean field theory, as indicated by the cartoon on the right. So there's spontaneous layer polarization, and so something very close to this is occurring in magic angle twisted bilayer graphene. So it turns out that this momentum space vortex core, if you like here, defined by the band eigenstates, cures itself by having the states near zero momentum spontaneously polarized to one layer or the other. And so there's spontaneously broken layer symmetry, which opens a gap. And I don't have time to comment too much on experimental manifestations of this, although I will say something in a minute. But to suffice it to say that in bilayer graphene, it's a very delicate thing. In fact, it's only seen experimentally in suspended samples, and it becomes more robust in magic angle twisted bilayer graphene, presumably partly because the bands are even flatter. So here's a cartoon from a paper around the time people were working on twisted bilayer graphene. And it shows in cartoon form that reminds us in cartoon form that there are 4 flavors of all of these states in these graphene systems: spin and valley. So spin labeled by up or down in this picture, and valley labeled by K and or K prime. And so the point is that you can break this crystal symmetry, layer symmetry, actually in bilayer graphene, independently in each flavor. And in a Hartree-Fock mean field theory, the flavors are mostly independent of each other. And so one important observation, which is coded in these pictures by the sense of chirality of these curves, is that when polarized to a certain layer, to one layer, states in these 2 valleys behave differently, and they behave differently with regards to their Berry curvature. I should have mentioned the Berry curvature is related, as you know, to the integral of, if you can imagine from my bad drawing here, as you integrate over momentum space, the integrated Berry curvature is related to how much area you cover on the block sphere, and turns out that through kindness of God, Berry curvature, which is a momentum space Berry curvature, is also an observable. The Hall effect of especially of insulators is just related to the integral of the Berry curvature. And so what these cartoons are indicating is that in AB bilayer graphene, you could say similar things for tetrahedral trilayers. For a given sense of layer polarization, the Hall conductivity, which is related to the momentum space Berry curvature, so-called anomalous velocity, is opposite for opposite valleys for the same sense of layer polarization. And that has to be true because these two valleys are related to each other by time reversal symmetry. So, when you have these four flavors, and if you assume a simple state in which a mass gap opens via this mechanism I tried to describe for each flavor, you can imagine states with a whole bunch of different total Hall conductivities. For example, the ground state appears to be of the system from experiment is thought to be basically a spin density wave system. And it's clear from both theory and experiment that there is an energy penalty for having a different sense of layer polarization for different valleys. So these two valleys here, K and K prime, have the same sense of layer polarization in the ground state of the system. And therefore they have opposite contributions to the Hall conductivity. So the actual ground state is spin density wave state. I'll say something more about some of these other states in a moment, but there are hints. For example, hints. This is a picture on the right is taken from one of the papers from Amir Yacobi's group in your department around 10 years ago in suspended bilayer graphene. And it's looking, if you look at the, I have to move that for me. If you look at the conductance measured at the top, this is, this experiment indicates that the, you're forming a state with Hall conductivity 2, churn number 2, in a very weak magnetic field. I think this magnetic field of this experiment, not sure if it's showing there, is less than 1 Tesla. Oh no, it's 1.56 Tesla. What is seen experimentally is that even though these states that have a net Hall conductivity don't appear at 0 magnetic field, are not the ground state. The ground state is either the antiferromagnetic state, or if you put on a bias voltage, which is what's displacement field in this direction, then it's a layer polarized insulating state, which are 2 of the states on the previous cartoon. But the states, the fact that this, these states with a net quantum anomalous Hall effect are, the fact that they're nearly the ground state, they're nearby in energy, is indicated by the fact that the quantum Hall effect of these filling factors persists down to extremely low magnetic field. And that's something that we've been trying to describe partly phenomenologically recently in a paper that's been sitting almost finished for a long time. This happens sometimes. Okay, so that is, that's A.B. Bernal bilayer graphene. I see I'm taking more time than I should. So part of my message, though, is that what I described there occurs more robustly in magic angle twisted bilayer graphene. For example, this is a plot with interaction strength on this axis and twist angle on this axis. And let me just emphasize that what's indicated on the right-hand side of this curve as the twist angle is coming down to the magic angle from above. And the interaction strength that's necessary to open a gap at neutrality, analogous to twisted bilayer graphene, goes down as you as you approach the magic angle, and the bands get flatter and flatter. Okay, so so here's a cartoon now, and this is now not bilayer graphene, by magic angle bilayer graphene. Here's the valence band, here's the conduction band, and in each flavor you can have a gap open up at neutrality, which is which supports a Hall effect, a flavor-dependent Hall effect. And what this cartoon is mainly emphasizing is that the main difference between magic angle twisted bilayer graphene, or one of the main differences, and just an AB bilayer, is that the density of states in an AB bilayer remains non-zero up to some large energy of order tens of EVs. But in the twisted system, you have just a finite number of states, one state per moiré period for each flavor in both the conduction and valence band sides. In the conduction band, and then there's a big separation between that, and there's a big separation between these states and the remote states. So, for example, the Fermi level has moved there to the case when none of the flat bands are filled. So that would be -4 electrons per moiré period. And you can move the Fermi level through this entire region. And this, at a mean field level, that finite width of the conduction and valence band, where it turns out all of the Berry curvature gets normally buried into that, is present within that single band. And so you have a single band which has a Chern number. And so what's new that can happen is that you can have non-zero filling factors. For example, this is the illustrating the case of filling factor +2. And so at some density that's not zero in magic angle twisted, or in AB Bernal bilayer graphene, nothing interesting happens. But in this case, you can simply fill all 4 bands for 2 of the flavors and leave the other 2 flavors in this interesting regime where they can open up a gap at neutrality and have these Chern insulator states. In other words, states with that support a quantum anomalous Hall effect, that have Berry curvature that integrates to a non-zero quantized value. And in order for this to happen, then the extra energy that these quasi-particles get by virtue of being occupied due to their exchange interactions has to be, bigger than the bandwidth. And so this is some kind of Stoner-like criteria for this state. And this state, as far as the flavors degree of freedoms are concerned, is some kind of generalized ferromagnet, which by which I mean it doesn't break translational symmetry, but it does break the flavor symmetry. So we can have states with non-zero Chern numbers not only at neutrality, but also at these other filling factors. And if the filling factor, the number of electrons per moiré period, is an odd integer, and we form a state of this type where only some of the flavors are completely filled or completely empty, and some other ones are half filled. If an odd number are half filled, then we have to get a Chern insulator state. There's no way to avoid it, basically. Okay, and yeah, so this is just a sketch which shows an estimate for Stoner criteria. The main thing here is, that there's a natural energy scale in these problems, which is maybe 20 to 50 millielectron volts or something. And so we expect these broken flavor symmetry states to appear when the bandwidth is less than, let's say, 20 millielectron volts. And that occurs over, a certain non-zero range of twist angles. And so I think this is what is being studied experimentally. And let me take a look at my time. Okay, I'll mention this. This is just a little curiosity. I ran across these papers from the 1940s by Heisenberg and London, and they were proposing a theory of superconductivity. And their argument was that if you occupy states in momentum space, that there's energy to be gained when you place the electrons close together in momentum space, something they called condensation in momentum space. And they argued that this could produce superconductivity, spontaneous currents, and they're partly right in the sense in that this momentum space condensation can break time reversal symmetry and lead to not to superconductivity, but at least to spontaneous circulating currents, which is orbital magnetism. And the reason they argued that you want to put states close together in momentum space is that the exchange interactions written in momentum space for long-range interactions are larger when the states are close together in momentum space. And this is basically more or less a statement of why there's a tendency towards spontaneous valley polarization in multi-valley semiconductors, and which in the case of twisted bilayer graphene, the bands are narrow enough that, that the symmetry is actually broken. Okay, so now I'm going to talk a little bit about what we know from experiment about, what experiment is telling us about where this flavor symmetry breaking takes place and what its properties are. So I'm showing you a color scale plot of resistivity versus magnetic field, and along the x-axis is carrier density, on the right neutrality, and on the left 4 missing electrons per moiré period. And this is only one experiment. People don't see the same thing every time, and some of the reasons why are known and obvious, but give rise to a large phase space that it's difficult to explore. Detailed properties depend on how far the gates are away and on exactly what the twist angle is, and maybe some other things that we haven't fully recognized yet, but maybe ideally mainly those two things. And but this is sort of a pretty typical type of observation. And what you see in this resistivity plot are Shubnikov to Haas oscillations, which, as you know, are a standard way of measuring Fermi surfaces. And so the experiment says there's a Fermi surface. System is behaving like a Fermi liquid when you start at neutrality and start taking electrons out. And indeed, if you look carefully at this pattern, you'll say that there are 4 degenerate Fermi surfaces that are being emptied. So there's no broken flavor symmetries according to this experiment until you get down to filling factor near -2, and then it looks like you have a Fermi surface again. It's actually a hole-like Fermi surface, so you're emptying a band. And so what has apparently happened here is that when you reach -2, you get an insulating state by completely emptying 2 of the 4 bands. And then when you take out more electrons, you have to make a hole-like Fermi surface in the 2 remaining bands. I won't talk about the other cases. So this is an example, and I'll show you some other examples in a minute of things we want to try to understand. Why does it occur like this? And it occurs in a very different way. As I'll mention a little bit later, if you go to the electron side where you add electrons to the moiré pattern. So why? And I'm going to talk, part of, my working assumption motivation for which I'm trying to share with you is that even though the energy bands in magic angle twisted bilayer graphene are very narrow, the dispersion that remains is playing an important role in the phenomenology that is seen experimentally. And here I mention this slide is intended to help me say one thing about something that is, so what I said is the remaining dispersion is important, but the model that we originally wrote down for bilayer graphene doesn't describe that residual dispersion well enough to describe what's going on. There's several corrections that are important. And so we try to describe those phenomenologically. We know they're important partly because of DFT work, much done at your university. But one of the things that's important is that the bands are not particle hole symmetric. And as pointed out to me by Stephen Carr, you can understand the way in which the bands are particle holes asymmetric, the way in which the valence bands are different from the conduction bands by just using this, simple tight binding model, sort of two-center approximation type binding model from which Rafi Bistritzer and I originally derived our simple picture for the electronic structure of bilayer graphene, that there's hopping from layer to layer, and you could represent it in momentum space. The approximation, natural enough, that we made in our simplified theory is that all of the momenta that we're interested in here are close to the Brouin zone corner. And so you could simply replace this hopping parameter. It's actually Fourier transform to real space of hopping between pi orbitals in different layers. Fourier transform to momentum space. You could replace it by its value at the Brouin zone corner momentum. And so then that has the attractive feature that the tunneling between the layers is characterized by a single number. And it also corresponds to tunneling between the layers. As you can imagine, if the momentum dependence is completely dropped, that means its tunneling is local between the layers. And so this non-local tunneling correction takes account of the fact that the tunneling between the layers is not local. When you go between layers, you go sideways a little bit. And with some approximation, you can also describe that, introduce one extra phenomenological parameter to account for that. And so main lesson is, the band structure has corrections. The non-local tunneling one I just explained, very well known, is that mainly because of strain effects in the bilayers when you twist it. The areas with close to AA stacking are expanded, and that appears in the model in terms of the AA tunneling parameter becoming larger. And finally, it turns out, as I'll explain a little bit more detail in just a moment, that there are important interaction corrections to the band that change as you fill up the band. And so here's a calculation. So this is something I know is right because it's just single particle theory, and it's a calculation of the Hall conductivity as a function of filling of the bands, and for 4 different band models. And so this is neutrality. This is the Hall conductivity expressed as Hall density, a Hall filling factor, the Hall density, which is basically the Hall conductivity, the Hall resistivity, if you like, or 1 over the Hall resistivity, is negative for hole-like Fermi surfaces, positive for electron-like Fermi surfaces. And one of the point I want to make is simply these differences in the band structure model, trying to correct, for example, if you start from the original model that Rafi and I wrote down, correct for strain effects, correct for non-local tunneling, correct for interaction effects I'll come to in just a moment. The bands keep changing, and I'm just using the Hall conductivity here as a convenient, experimentally accessible index, if you like, of the band structure. For example, this picture says Fermi surface changes from hole-like to electron-like once as you empty the valence band and once as you fill the conduction band. The actual filling factors at which these changes in sign of the Hall conductivity are, turns out, not exactly at Van Hove singularity points, but close to. And it changes sign from hole-like to electron-like once as you empty the band, once as you fill the band, and at very different filling factors on the electron side and the hole side. And I think that difference in filling factor is manifested in the experiments. Maybe I don't have time to comment on that. So this is showing the interaction effect, and I'll give a partially correct qualitative explanation for this. These are non-interacting bands that I showed you before. And the bands in blue are what the bands look like. They change as you empty the band just through mean field effects. And the biggest part of this is that wave functions at different momenta in the Brouin zone are actually more strongly peaked in different parts of the moiré pattern. And most of the states in magic angle twisted bilayer graphene are actually peaked near the AA points in the moiré pattern, whereas these wave functions here near the gamma point are less localized in that region. And so it turns out that you change the shape of the bands for that reason as you empty them, and that when the bottom of the valence band is close to the Fermi level, it's very flat. And when the top of the conduction band is close to the Fermi level, it's very flat. And that's also manifested. Let me just skip those. Okay, so I talked about the Hall density as a index of the electronic structure. Here's an actual Hall experiment. This one is actually from Andrea Young's group. You can find in the literature similar data from many different groups, many different samples, and they don't all look exactly the same, but they tend to look kind of similar to each other, and this is a fairly typical one. And first thing you notice is this is plotted as Hall density here. I could have done it as Hall filling factor, but this is actually experimental data, sorry. So you can see that it doesn't look like the what I showed you before from theory. It's supposed to change sign from, on the valence band side, from negative to positive once, corresponding to a change from a hole-like Fermi surface to electron-like Fermi surface. Instead, what it does is it's hole-like, and then it's something complicated happens, and then it's hole-like again. And so you can see that this Hall data is very consistent with the Fermi surface data. Here I have hole-like Fermi surfaces. They're close to half empty, and then I jump to another state where I take 2 of the 4 flavors and completely empty them, and then I start emptying the remaining 2. On the electron side, something similar happens, but it happens at much earlier, much smaller filling factor. And so schematically, this is, I think, what both of these experiments are telling us, that there is a very high density of states region within the bands close to these Van Hove singularities, and the electrons don't want to have a metal with a Fermi level close to these Van Hove singularities. So if I start off, for example, at neutrality and start removing holes, I have 4 degenerate Fermi surfaces, and eventually when I get close to half emptying the bands, the Fermi level is moving close to this Van Hove singularity, which appears rather deep in the bands on the valence band side. And then it apparently does something complicated happens, but it eventually goes over to this simple state in which I only have 2 Fermi surfaces left. The other 2 valence bands have been completely emptied, and then I seem to follow this curve, and it's always a little hard to understand and experiment what's going on. Very close to empty, very close to full, and whereas on the conduction band side, and I start to occupy the bands, I don't get very far before the Fermi level gets close to the very high density of state region, and therefore much sooner as it fills the valence band, it jumps to a state with completely fills one of the 4 Fermi surfaces, leaving 3 remaining ones. And yeah, let me just skip that. Okay, so here is a theory calculation. This is actually not done with the band structure that fully reflects this particle hole symmetry, but this is energy as a function of filling factor. Whoops. The green line is not allowing symmetries to break, so there are always 4 identical Fermi surfaces. And the yellow line is allowing them to break in pairs. 2 flavors have different filling factor from the other 2 flavors. And the general case where all 4 flavors are allowed to separately optimize their filling factors is that definitely gives the lowest energies in a region not restricted to integers, but in a region of filling factor, a broad range of filling factor, which includes metallic states. Yeah, so one thing you can notice here in these mean field calculations, if you look at the slopes of these lines, energy versus density, when they come together, it seems like they're coming together with the same slope nearly. And so that's to say that these phase transitions between these states in these calculations are sometimes continuous or nearly continuous. And indeed, that's what it looks like experimentally too. If you look, for example, at these these experiments on inverse compressibility d mu dn as a function of density. Normally, when we have a gap, we have a big peak in d mu dn, but that seems not to be the main thing that's seen in these experiments. Instead, you see a jump in the chemical potential the way you would expect at the mean field description of a continuous phase transition. Okay, so I have, I guess, 2 minutes left, and I'm not going to comment on the observation of the anomalous Hall effect. I noticed on your schedule that you have David Goldhaber-Gordon visiting next week, who was the first person to see orbital ferromagnetism and anomalous Hall effect in twisted bilayer graphene. I'm just going to lightning step through these slides and make one observation. One is that one thing that's very interesting about orbital magnetism is orbital magnetism, and you can think of the quantum Hall effect as more or less a measurement of this, says that the magnetization depends on chemical potential even within a gap of an insulator, and that doesn't happen in, of course, a regular spin magnet, and that has been seen apparently experimentally in recent experiments on these. This is actually a bilayer graphene system, but what these experiments show is that for a state with a given sense of Valley polarization, the sign of the orbital magnetization changes when you go across the gap from one way to another. And so last thing I want to mention here is, the million-dollar question, the hardest question, and therefore, it's good that I don't have too much time left to talk about it because I'm working on it, but I don't understand very much, is with any confidence, is superconductivity. And what's behind superconductivity? So obviously it could be phonon mediated. I think that's certainly cannot be ruled out in these systems. A related way in which the phonons are manifested experimentally is in the resistivity. This is a calculation done by Wei Chin and my group of temperature-dependent resistivity. Without going into detail, you can see these temperature-dependent resistivities have a slope that increases with temperature, whereas experimentally, the resistivity seems to, throughout the magic angle twisted bilayer graphene regime, be nearly linear in temperature, as if there were some really low energy collective modes stuck down in the low density regime. And so since phonons can't explain the resistivity, maybe they don't explain the superconductivity either. And one possible culprit are these flavor fluctuations. And so this is a scenario that we're working on right now. So we know that there are, this is not the correct archive number here, but you can find this paper under the name of Ajesh Kumar. And one of the interesting things is in a mean field calculation where you have a nice ordered ground state at zero temperature, even though you're not, I haven't emphasized here, but as known, especially at Harvard, that you can't make Wannier functions very easily in these flat band states. The collective modes don't seem to care. You get a whole bunch of collective modes as if you had, collective modes look like, just like you had a localized object on each side in the insulating states, which carries a conduction valence, orbital degree of freedom, and a spin and valley label. And so you have lots of low energy collective modes. And these are a good candidate as the explanation for the superconductivity, but I certainly wouldn't claim that that's known yet. So let me just leave these conclusions up and stop here.
Okay, well, thank you very much. We have time for some questions. Either perhaps a good way to do that is to write a note into the chat. If you look at the bottom of the screen, it says chat, sort of a note, or you can speak up and we'll try to recognize you in the set of people there. Okay, here's one from Zoe Shu, panelist. In the band structure, including interactions, is there a small symmetry breaking at K and K prime? I noticed small gap openings. Also in the title of the same figure, delta T equals 20 MeV. Is this an empirical correction to the hopping parameter due to the momentum dependence? Question mark.
Yeah, so the first question, I think the answer is no, but I may be forgetting a little detail there, but it's certainly very small. So second question, delta T we viewed as a empirical fitting parameter. But if you look at some generic guess for the non-locality of pi orbital to pi orbital tunneling and some kind of sensible two-center approximation, then the rate at which the Fourier transform of that tunneling as a function of distance, the rate at which it falls off with Q is in the same ballpark. Yeah, so if you had to guess what it was, and I think also, if you had to guess what it was at this level of a two-center approximation, you'd guess something very similar. We haven't gone through the exercise of trying to figure out, what's the best fit to ab initio DFT, but I'm pretty sure it's on the same ballpark.
Okay, thank you. Another question from Yasheng Wang. It says, can you elaborate a little bit on the phonon limited resistivity?
Okay. So this is, this is a pretty straightforward calculation in which we take the phonon modes as being localized in the two graphene sheets, and don't include the moiré influence of the moiré pattern on the phonon modes. We just calculate the resistivity as a function of temperature, from occupation, from scattering, from a lifetime, if you like, electron phonon scattering lifetime of states on the Fermi surface, which are, of course, changing quite a bit as a function of filling factor. And, maybe the main point is that, you might think that if you had a small Fermi surface, the biggest phonon momentum you could get would be proportional to the size of the Fermi surface. And therefore, the biggest phonon energy you would get would be, speed of sound times that momentum. But that ignores the fact that the band wave functions are not plane waves. They have all kinds of higher momentum components involved in them. So electrons are on the Fermi surface are scattered by phonons out to large momentum. And that's why the resistivity d rho dt, if you like, just keeps going up as you go to higher temperatures.
I see.
So this is described in detail in a paper that we'll put on the archive pretty shortly.
Okay.
But there, yeah, I think there's other similar papers out there.
Okay, great. Any one last question? Okay, if not, thank you very much, Alan.
And,
very interesting.
Thanks to everyone for listening, and thanks to you for hosting, Bob.
Okay, great.
Right.
Well, that's great. Thanks so much. And we'll wind things up here.
Yeah. Okay, bye-bye. Thanks, everyone.